Okay, welcome to chapter 4.8, analyzing graphs of polynomial functions. The essential question for this section is how many turning points can a graph of a polynomial function have? A turning point of the graph of a polynomial function is a point on the graph at which the function changes from increasing to decreasing or decreasing to increasing. So let me explain that really quick with a highlighter. And green is positive, so let's do that one. So it is... I narrowed it, but I guess it ignored my narrowing. All right, so it is what is this doing? It is increasing from here to here. This is where it's increasing. Okay, try that again. It is increasing here until it gets to that point right there. It is increasing here until it gets to that point right there. So this is going up from there to there. And then finally, this is as close to red as I have. And this is going to decrease here. It's going down from here to here. So it's increasing, decreasing, increasing, and therefore there are two turning points. And this is a relative maximum, and this is a relative minimum. So what you will learn in this chapter is use the x-intercepts to graph polynomial functions, use the location principle to identify zeros of polynomial functions, okay? And find turning points and identify local maximums and local minimums of graphs of polynomial functions. And then finally, identify even and odd functions. Okay, so we're going to go in deeper and graphing more precisely. Rather than just finding y-intercept and x-intercepts, we're now going to find the turning points and identify if the function's even or odd. Okay, so graphing polynomial functions. In this chapter, you have learned that zeros, factors, solutions, and x-intercepts are closely related concepts. Here is a summary of these relationships. So the concept summary states that zeros, factors, solutions, and intercepts. Let f of x be a polynomial function. The following statements are equivalent. 0. K is a zero of the polynomial function f. Therefore, the factor would be x minus that k, and that's a factor of the polynomial f of x. Solution. K is a solution or root of the polynomial equation f of x equals 0, and x-intercept. If k is a real number, then k is an x-intercept of the graph of the polynomial function f. The graph of f passes through k comma 0. So the key factor to that is right here. If k is a real number. If it's an imaginary solution, it's not an x-intercept. So it's the only difference. So solutions, roots, zeros, x-intercepts all mean the same thing unless we're talking about imaginary. And a factor is just the zero subtracted from x. So x minus whatever that zero is a factor of the polynomial. Okay, so let's put this to work. Example 1, using x-intercepts, graph a polynomial function. So here we have a polynomial function. F of x equals 1 over 6 times x plus 3 times x minus 2 squared. Okay, so here's step 1. Step 1 is plot the x-intercepts. All right, so the x-intercepts is when x equals -3 and when x equals 2. Because x minus k is a factor, then k is the x-intercept. So I'm going to put a point at -3, and I'm going to put a point at 2. Okay, that's pretty straightforward. And so those are the two x-intercepts. It either crosses or it bounces. Well, we do know that it's going to bounce because of this squared. So when there's a multiplicity of 2, that is going to bounce off of the x-axis. So is it above or is it below? So we're going to figure all this out. Okay, so step 1 is done. We plotted the x-intercepts. So now step 2 says to plot points between and beyond the x-intercepts. So what that means is we want to create a table of values. Okay, so let me just do this. and I'm going to choose values between and beyond. So let's start with -4. So if I substitute in -4, I'm going to get -4 plus 3, which would be -1, and -4 minus 2, which would be -6. -6 squared is 36. Okay, so 36 times a -1 is -36 times 1/6, which is the same as divided by 6, would be -6. So I have -4, -6. So that's down here somewhere. Okay, so this is really difficult for me. This is the hardest part of doing this, and that is getting my pen to come up like a function would. Okay, so it's something like this, and that's what we know so far. And this is continuing down, I believe. All right. And then we don't want to plot -3 because we already know it's 0. So how about -2? So I put -2 in my table, and let me erase these. And now -2 plus 3 is 1, and -2 minus 2 is -4. -4 squared is +16, times 1 is 16, divided by 6, which is 8/3. 6 is 8/3, which is 2 2/3. So if I go to -2, I'm going up 2 2/3. So my point is -2, 2, 1/3, 2/3 approximately here. So there's 2 2/3. Okay, so now I know this function is continuing up to this point. Ooh, this is difficult. Okay, so it's coming up like so. I don't know what it's doing beyond that, so I'll just wait for now. And I want to choose -1 next. So I'm going to put in a -1, erase this, and -1 minus 2 is -3. -1 plus 3 is a +2. -3 squared is 9. 9 times 2 is 18. 18 divided by 6 is 3. Hopefully you're following this mental math. And so -1 up 3 is right here. So this did continue up through this point and is turning and going towards this point. So now we're here. All right, so we're making progress. Now I want to try 0. Well, if I plug 0 in here, I get 3. And if I plug 0 in here, I get -2. -2 squared is 4, times 3 is 12, divided by 6. 12 divided by 6 is 2. Okay, so if I put a 0 in, I get 2. So there's my y-intercept, 0, 2. So in order to get from here down to here, this had to turn. All right, so now I'm here. So then I choose one more point, 1. And if I substitute 1 into this equation, I get 1 plus 3, which is 4, and 1 minus 2, which is -1. -1 squared is 1, times 4 is 4, divided by 6 is 4/6, or 2/3. So I'm going to go over 1 and up 1/3, 2/3 is right here. So now this is coming down like so, and it's continuing down to our x-intercept. And I'm going to do one more point, and that's going to be 3. So let me move all these and just slide them up a smidge. Okay, and that way I'll have room for my 2 and 3, or 2 and whatever it is. So I put a 2 here. I erase this. 2 minus 2 is 0. I don't care what this is, but it is 5. 0 times 5 is 0. Okay, and actually, why am I putting 2 in? Because I already knew it was a 0, so let's get rid of that. But that confirmed it. Let's try 3. So if I put 3 in here, I get 3 plus 3, which is 6. If I put 3 in here, 3 minus 2 is 1. 1 squared is 1. 1 times 6 is 6. 6 divided by 6 is 1. So I get the point 3, 1, which is right here. So it's turning and going back up. Okay, and it is going to continue to do that. So there is the graph of our function with a turning point at -1, 2, or 3, and a turning point at 2, 0. Okay, so step 3 is to determine the end behavior. So looking at this, this is degree 2, this is degree 1, totaling a degree of 3. So degree 3 functions can either do this or go down, up, down. And obviously A is positive, so this is what it should look like. So the end behavior is, I'm going to write this, as x approaches negative infinity. In other words, if I'm standing here, okay, and I go this direction, walking as I go this way, I have to look down to see where the function's going. So as the function is, as x is going to the left, comma, the function is approaching negative infinity. So as I'm going this way, I have to look down. But then if I, hopefully this isn't all one piece, it is. So then if I am going this direction, I have to look up. So that's as x goes to positive infinity. You can put a plus in front where you don't have to. F of x is approaching. Let me clean that up a little. So as we go to the right, the function's going up. So there's the end behavior, and this is going to determine where this function goes after all of our turns, if you will, our turning points. So there's the step 3. And then step 4 is just to draw the graph so that it passes through the plotted points and has the appropriate end behavior. So I was doing that as I went, and I should probably highlight that point there. And this point here, those are key points. X-intercept, maximum or turning point. Y-intercept, minimum, relative minimum or turning point, and then turning and bouncing because it's a double root and going to positive infinity. Okay, so now that I've done that, you should be able to do problem 7, 8, and 10. Okay, the location principle is the next concept we're going to talk about. And it says you can use the location principle to help you find real zeros of polynomial functions. So the core concept states that the location principle, if f is a polynomial function and a and b are two real numbers such that f of a, the function, is negative and f of b is positive, then f has at least one zero between a and b. So let me go back to the last. Let me go back to the last page, and let me get rid of this guy here. Actually, it was all one piece. So how about I just click here and delete and delete. Okay, so what they mean is location principle states that if f of negative 4, okay, if f of a, f of negative 4 is negative, and f of b, which is f of 2, is positive, then there has to be a zero between a and b. Okay, so let me clarify that. When I substituted in negative 4 into this function, I got negative 6. When I substituted in negative 2, I got positive 2 3/4, 2/3, 2 2/3. That is positive, that is negative. In between a negative and positive, there must be a zero. So we know that there is a zero between negative 2 and negative 4. And in this situation, it was an integer, but it doesn't have to be. But that's what this principle means. Okay? To use this principle to locate real zeros of a polynomial function, find a value a at which the polynomial is negative, and another value b at where the function is positive. And you can conclude that the function has at least one real zero in between those 2 points. And that is the location principle. Okay, example 2, locating real zeros of a polynomial function. It says to find all real zeros of f of x equals 6x cubed plus 5x squared minus 17x minus 6. So in this situation, we're not going to try to factor this. So there's no GCF here. We'd have to find factors using the remainder theorem. You'd have to find factors of -6 divided by factors of 6 and do synthetic division over and over to break this down and find roots and solutions. In this example, they want us to use a calculator. So I have the TI-84 over here, and f of x equals 6x cubed. So I'm going to start with that. I just want to get a mental picture of what we're working with. It is a cubic 3210. It's in standard form. It's a cubic with a positive leading coefficient. So it's a cubic, so it looks like this, and it's going up to the right forever and down to the left forever, our end behavior. As x approaches negative infinity, the function approaches negative infinity. And as x approaches positive infinity, the function approaches positive infinity because this is positive cubed. All right, so I know what it's kind of going to look like. Just got to find where it crosses the x and y axes and where our relative max and mins are. Okay, so in order to do this with a calculator, the first thing we're going to do is make a table. So what they mean by that is you go into y equals, and you put the function 6x, and then I hit math 3 for cubed, plus 5x squared minus 17x minus 6. So I put the function in y equals. So I hit y equals and plug that function in. And now I want to go to a table. So I see how table's blue here. So I use my blue second button and the graph button to get my table command. So I hit second table, and it's blank. So I'm just going to plug values in. 0, enter, 1, enter, 2, enter, 3, enter, 4, enter, 5, enter, and 6, enter. So what I want to point out here is when I plugged 0 in, I got a negative. When I plugged 1 in, I got a negative. When I plugged 2 in, I got a positive. Ding, ding, ding. I went from negative to positive. So there is a 0 between 1 and 2. Okay, so that there is the first thing that I notice. So using the location principle, I have a 0 between 1 and 2. Okay, so let's take a look at the rational root theorem really quick. So what I do is I take factors of 6, which are 1 times 6, 2 times 3, or it could be -1 times -6, -2 times -3, over the same factors. So if I put 1 over 1, I get plus or minus 1. If I put 1 over 2, that's plus or minus a half. 1 over 3, plus or minus a third. 1 over 6 is plus or minus 1/6. I could have plus or minus 2 over 1. Plus or minus 2 over 2, which is 1. That's already there. So I'm going to skip. I'm not going to rewrite any. Okay, so I'm doing 2 over 2, which is 1. And then I do plus or minus 2 over 3, plus or minus 2 over 6, which is a half. I mean a third. So that's already there. So I'm done with the 2's. So then I'm going to do plus or minus 3, plus or minus 3 over 2, which is 3 halves, plus or minus 3 over 6, which is a half. It's already there. So my 3's are done. And then I'm going to do plus or minus 6 over 1, plus or minus 6 over 2, which is 3, plus or minus 6 over 3, which is 2, and plus or minus 6 over 6, which is 1. So I'm done. These are all my possible roots right here. 1, 2, 3, 4, 5, 6, 7, 8. Positive, negative makes 16 possible roots. So why am I doing this? Because I now know that there is a root, a solution between 1 and 2. So between 1 and 2, plus or minus 1, or between 1 and 2, since it's positive, it's none of the negatives. 1 is not between 1 and 2, a half's not between 1 and 2, a third is not between 1 and 2, and a 6 is not between 1 and 2, so it's none of these. 2 is not between 1 and 2. 2/3 is between 1 and, no, it's not between 1 and 2, it's less than 1. 3 is not between 1 and 2. 1.5 is between 1 and 2, so there is our solution. So now I know that it's 3 halves. So if I put that in my calculator now, all right, and I put 3 divided by 2, I should get 0. And sure enough, there it is. There's our 0. Okay, so that's what you need to do with these problems. You have to be able to identify this type of stuff. So use a graphing calculator to make a table. That is done. The next step is use the location principle from the table to show you can see that f of 1 was negative and f of 2 was positive. So by the location principle, we have a 0 between them, like I just stated. So if f is a polynomial function of degree 3, it has 3 zeros. The only possible rational 0 between 1 and 2 is that 3 halves, and I explained that using the rational root theorem. Okay, so using synthetic division, you can confirm 3 halves is a 0. Okay, and so what they mean by that is, let's do it. So what you do is if 3 halves is a 0, then you would take negative 3 halves. Okay, the solution to that, and our polynomial is in standard form, not skipping any 3, 2, 1, 0, and my coefficients are 6, 5, negative 17, negative 6. So you do this, bring down your first term, and negative 18 divided by 2 is negative 9, and that gives me negative 4. Negative 4 times a negative 3 is a positive 12, divided by 2 is 6. Negative 17 plus 6 is negative 11. That'd be negative 33 over 2, and that's not going to give me a 0. If I do positive 3 halves and do the same thing, bring down the 6. 6 times 3 is 18, divided by 2 is 9. 9 plus 5 is 14. 14 times 3 is 28. 42 divided by 2 is 21. Negative 17 plus 21 is 4. 4 times 3 is 12, divided by 2 is 6, and I get a 0. So now I know I have 6x squared plus 14x. It snapped for some reason. 14x plus 4 times 2x minus 3. These are our two factors of that polynomial. So it says using synthetic division, I can confirm that 3 halves is a 0, and I did right there, putting 3 halves in as a synthetic division factor. Okay, so what do we do next? We want to write f of x in factored form, which I just did. So it's x minus 3 halves is how the book is showing it. But if I bring the denominator over, it's this. So basically what the book is showing is the same thing, except they did this. They left it in a fraction form. And we have 6x squared plus 14x plus 4. The book does not explain where this came from. And these are all even, so I can factor out a 2. X minus 3 halves. Divide all this by 2. I get 3x squared plus 7x plus 2. Okay. Factoring that, I get 2 times x minus 3 halves. And I want factors that so this will work. And here is how I do it. I take a times c and rewrite it as x squared plus 7x. I get rid of this 3 and move it back here and multiply and get 6. And this I just think is a lot easier to find the roots. So this is going to come down to x minus 3 over 2. And then I'm going to get factors of 6 that add up to 7 are x plus 6, x plus 1. But don't forget, I divided or multiplied by 3, so I need to divide by 3 when I'm done. Okay, and this is going to simplify to 2 times x minus 3 halves. That comes down. 6 divided by 3 is 2. Whoops. 6 divided by 3 is 2, so I just write that as x plus 2. And then I get x plus 1/3. The 3, since it can't be simplified, I move it to the front, 3x plus 1. So there are our factors, and that is what the book is showing in this step right here. Okay, so 2x minus 3 halves, 3x plus 1, x plus 2. The order of your factors doesn't matter because multiplication is commutative. Okay, so now that we know all the 3 zeros from that factored form, we can finally confirm that we have zeros at 3/2, which is here, -2, and -1/3. And check this by graphing. So then I just go to my calculator and hit graph. And voila. So this isn't really clear. This is -1, this is -2. So how about I change my Y window to the left, or my X minimum to -3, so I'm not going all the way out to 10. Okay, so there it is. And this is only going out to about 2, but I'll do window and I'll go X max 3. And so I'm just trying to show you how to manipulate your graph. I'm not seeing where this maximum is. It's a little higher than 10. So I'm going to try Y maximum of, let's say 13 and see if that does it. And it stays on the screen. Very good. But we're missing our relative minimum. So I need to go lower on the Y axis. So I'm going to change my Y minimum to a lower number. How about -13 as well? But that might not do it either because it seems steeper there. And sure enough, I'm still off the screen. So I'm going to go to -15. Okay, so now let's see what that looks like. So there it is, beautiful. So there is the function that we started with up here. 6x³ plus 5x² minus 17x minus 6. So here's -6, that is our y-intercept. We have a 0 at -1.5. Okay, I'm sorry, -1/3 is here, -2 is here, and 1.5 is right here. So we confirmed that these 3 zeros are in fact here, here, and here. Y-intercept is here, and we could find our relative maximums and minimums by finding values between our zeros. Okay, so now that I've done that, you should be able to do problem 17, 18, and 20. Okay, now we're talking about turning points. Another important characteristic of graphs of polynomial functions is that they have turning points corresponding to local maximum and minimum values. Okay, the other term that I've seen in math textbooks is relative. Relative maximum, relative minimum. Okay, but local and relative are relative. The y-coordinate of a turning point is a local maximum of the function when the point is higher than all nearby points. So this point right here is higher than this point. It's higher than this point. It's higher than this point. All points around it, it is the highest point of the points around it. The y-coordinate of a turning point is a local minimum of a function when all of the points in the when the point is lower than all nearby points. So this point is near it, it's higher. So this point is lower than all the blue points I'm drawing. So the lowest point in a group of points in a certain area of x values. The turning point of a graph help determine the intervals for which a function increases or decreases. Okay, so the core concept here says turning points of polynomial functions. The graph of every polynomial function of degree n has at most n-1 turning points. So let's give you an example. Let's just talk about parent functions. Let's say I had f of x equals x³. Well, my n is equal to 3 in this function. So n-1 would be 3 minus 1, which is 2. So if I have a cubic, it goes like this. So how many turning points does it have? 1, 2. 1 less than the degree. That's what that means. If a polynomial function of degree n has n distinct real zeros, then its graph has exactly n-1 turning points. So the degree of this is 3. The number of possible zeros is also 3. The number of turning points is 1 less than the number of zeros. So look at this diagram up here. Here is a 0, here is a 0, and here is a 0. That is 3 zeros. And as you can see, there is 1, 2 turning points. Okay, so this just says it has 1 turning point, 1 less turning points than it does zeros. That's all that states. Okay, So one less than the degree, one less than the number of zeros, because the degree equals the number of zeros. Okay, example 3, finding turning points. Now we're going to focus on the turning points. So it says graph each function, identify the x-intercepts and the points where the local maximums and local minimums occur. Determine the intervals for which each function is increasing or decreasing. So we're given a cubic in part A, x cubed minus 3x squared plus 6. And I always think about what that's going to look like before I even begin the process. And it's a cubic and it's positive, so it's going to look like this. So end behavior, I already know. As x goes to negative infinity, the function goes to negative infinity. And as x goes to positive infinity, x goes to positive infinity. There's a possibility of at least or 3 real solutions at most. The maximum number of real solutions is 3, and it has at most 1 less than that, 2 turning points. Okay, so that's just a recap of everything we've discussed. And so here's the solution. It says use a graphing calculator to graph the function. So I'm going to do that. So it's going to be x math 3 for x cubed minus 3x squared plus 6, and I hit graph. Okay, and there's the function. I can see both the relative maximum and minimum and the one real solution. So I now know it has 2 imaginary solutions because it has a total of 3 solutions. Okay, so I'm going to zoom in here and I'm going to change my window to x minimum of -3. So I'm going to put -3 in there and hit graph. I just want to get a closer view of this, and I don't care about what's going on 1, 2, 3, more than 4. So I'm going to change my x max to 4. And this will just zoom us in a little bit better. So now I can see where it crosses the x-axis. It's not crossing here, it's crossing the y-axis there. And so it says to use a graphing calculator to graph it. Check. The graph of f has 1 x-intercept right there, a turning point here, and a turning point here. Use the graphing calculator's 0, max, and min features to approximate the coordinates of the point. So I'm going to show you how to do that now. I want to find a 0. You hit, see that calc right there in blue? Use the trace button to get that command, but you need the second button because it's blue. So second trace is calculate. Let's find 0 first. So you arrow down to 2. I'm looking for a 0 of the function. I hit enter. It says left bound. I want my cursor to be the left of this 0 right here. So well, to the left is below the x-axis. So I'm to the right, I'm to the right, I'm to the right, I'm at it. Now I am to the left of this 0 here on the x-axis. That's what that means. So I hit enter. So it put a little arrow here. So now I want to tell it what range I'm looking for, or what part of the domain I should say, in the function. And now it says right bound. Well, if this is a 0, this is to the right of it. So I'm to the right now, and I hit enter. So I know my 0 somewhere between these 2 arrows. That's what that means. And the 0 is. So I hit guess or enter. And my 0 is approximately -1.2. So I'm going to write that over here. I'm going to say x is approximately -1.2. Okay, so I found the 0. It's an approximation. 1.20 is my approximate 0. It's actually 1.195823. All right. So the next thing I'm going to do is find the maximum and minimum, doing the same thing. So now I'm going to hit second, calculate. I want a maximum first, so I hit enter. And again, I do left bound, right bound. The maximum is right here, the local maximum. I am to the left of that maximum, and that's what this says, left bound. So I hit enter. It put a little arrow up there in my domain. I arrow to the right of that maximum over here, and I hit enter. So now I know that maximum is between those 2 arrows. That's true. So it says guess question mark. So I hit enter. And it says the maximum is approximately -1.8. Well, when I get this really big number, e to the -6, that's really close to 0. That's what that means. A lot of students get confused with that. So the maximum is at 0, comma. And by the way, if this x is -1.20, it's the point -1.20, comma 0, since it's a x-intercept. And this is a y-intercept, or is it? Yeah, it looks like the y-intercept. And the answer is 6. And sure enough, if you look up here, my y-intercept is 6, and that happens to be the relative maximum in this case. Okay. All right, so now I want to find the relative minimum. Second, trace to get my calculate command, and now I want a minimum. Arrow down to 3, hit enter, and I want to be to the left of this point here. So I want to get closer, though. I like to be near it. So if I just keep hitting this or holding it, and it will get close to that point. I am still left of that. So I hit enter, it puts the arrow there on my domain, and I continue to be, oops, stop. Oh no, oh no, oh no. Something happened, pause, it locked for some reason. Okay, so I just learned something. Don't hold this button down because then I can't stop it. I had to close the calculator and re-enter everything. So let's do that again. I'm looking for a relative minimum. So I hit second, calculate minimum, which is 3. Enter. I want a left bound, which is right here, enter. And I want a right bound. So I go to the right of that minimum, which is there. So I know that minimum is between these two. So I hit enter, and my relative minimum or local minimum is the point 2, 2. Okay, so whenever the graph gives you the calculator gives you a number like that, 1.9999, that's really close to 2. It actually is 2. So if I plug it in, I'd get 2, 2. So that is where my minimum is, my relative minimum. Okay, so with that being said, we are now, the x-intercepts of the graph is approximately negative 1.2. The function has a local maximum at 0, 6 and a local minimum at 2, 2. So I should say that local max, local min. Okay, the function is increasing. So now we have to talk about where the function's increasing. So it is increasing from negative infinity to 0. And that's what this means. Where x is less than 0, the function's increasing. X is less than 0 is over here. This is coming up, 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 up until we get to x equals 0. Then it hits a maximum. And then it's decreasing from 0 to 2. So, and that's what it says here, decreasing when x is between 0 and 2. So between 0 and 2, it's decreasing. And then you could also say x is increasing after x is greater than 2, and it says that right there. Okay, so that's what you need to state: increasing, decreasing, increasing, and state the locations of your domain where that is occurring. And then the next step is to do it again for part B. Okay, so let's do that. And let's see, am I recording right now? I am. Okay, so I'm just making sure. So I'm going to go to y equals and clear that. Now I'm going to graph this. So it's x to the 4th power minus 6x cubed is math 3 plus 3x squared and plus 10x minus 3. Okay, so 4, 3, 2, 1, 0. It's in standard form. And my leading coefficient is positive. So what is this function going to look like? It is going to be a quartic that's positive. End behavior, as x goes to negative infinity, it's increasing. As x goes to positive infinity, it's going to positive infinity. Okay, so there's my end behavior. I know it has at most 4 real roots. Okay, and here we go. So I'm going to hit zoom 6 to go back to my 10 by 10. And let's take a look at what happens. So there is my graph. And okay, so now let's talk about the window. -1, it looks like, is a solution. So I'm going to go out to -2, and that's it. So I'm going to change my x minimum to -2. I'm just trying to get a clearer picture of this. Okay. And then I see that it doesn't go out any further than 1, 2, 3, 4, 5. So I'm going to go to 6 on the maximum x. So I'm going to go to 6. So I'm doing one at a time. So now my function looks like this, and then it shoots up there. So now I just need to go lower to see my minimum over here. So that means my y's got to go lower than -10. So let's try -20 at first. I don't know where it is. And using a calculator, it's fairly easy to find it by doing this. Okay, still not far enough, as you can see. So I'm going to go by 10. So I'm going to go to -30. Okay, this is a really large number on the negative end. Okay, so here we go. And I'm still not there. So I'm going to go to -40 on my minimum. See if this does it. And not quite yet. So I'm going to go to -50. And so here we go. Hopefully this will turn on the screen and go back up. And sure enough, it did. So now I can see I have 1, 2, 3, 4 x-intercepts, which means I have 4 real solutions. And that's what I was looking for, up to 4. And it does have 4. There's no imaginary solutions to this. Okay, so what are we asked to do? Determine the intervals for which each function is increasing or decreasing and find the local maximums and minimums. Identify the x-intercepts. So it's going to take a little while. I want to find this x-intercept. So I hit second, calculate 0. And I want to be to the left of that first 0 over here. So if I move my cursor to the left of that 0, I'm going to be on the positive y value. So I'm above the x-axis here, hit enter. Then I want to go negative. I hit enter. And my x-intercept is -0.89. Let me change to red. So x is... You did see me click on that red, right? Okay. Red, red, red. X is approximately -0.89, comma, -4.62. Oh, I didn't hit guess yet. My fault. Hit guess after you do that. And the 0 is -1.13. My pen is not working well. All right, so -1 struggle's real. -1.14, comma, 0. Again, you see this -1 e to the -12. That means 0.000000000 go out 12 places. And so actually that really is a 0. So -1.14, comma, 0 is 1. Keep doing this. There are 4 of them. Second, calculate a 0, enter, move my cursor to the, move my cursor to here. That's to the left of the next 0. Now I'm moving above the x-axis there, hit enter, and hit enter again. And my 0 is 0.289. Okay, so I shouldn't say x equals. These are points. So my next 0 is approximately 0.289, comma, 0. Okay, and now I'm going to do it again. Second, calculate 2 is 0. And now I want to go closer to the next x-intercept. I'm to the left of it. I hit enter. I move it till I'm below. I'm to the right of it. I hit enter and hit enter one more time. And it's 1.82 approximately. So it's 1.82, comma, 0. And there's one more. So I'm going to hit second, calculate 0, enter. Move my cursor all the way down and over. Focusing on the zeros first, then I'll do the local max and min. So I'm to the left of that 0, hit it until I'm above, hit enter, enter, and I'm at 5.03. So it's 5.03, comma, 0. And these are all approximations. It's rounded. Okay, so there are my 4 zeros. And now I want to find the relative maximums and minimums. So when I hit second, calculate, actually, let me go back to the graph. Let's work left to right. So here's a minimum here. So I'm going to hit second, calculate, 3 for minimum. Move my cursor all the way back. Do-de-do-de-do. So sometimes I would just work left to right and do a 0, then the minimum, then a 0, then the maximum, then a minimum, and then a maximum. And that way I'm not moving the cursor so much. So I'm to the left of that minimum, I hit enter. I need to get to the right of that minimum. I hit enter again, and I get the point negative 0.57 is an approximation. So min, and it's a local min, and it's negative 0.57, comma, negative 6.51. Okay, so there's one of them. And then I move the cursor. Whoops, second, calculate. Now I want a relative maximum. That's 4. Enter. So now I'm going to go over here. I'm to the left of the maximum right there. Hit enter. Keep going, keep going, keep going. Now I'm to the right of that maximum. Hit enter, hit guess, and it is 1.11. So this is 1.11, comma, 5.12, 5.11, 5.11. So that's the relative max or local max. And continue, and we have one more minimum. Remember, we have 4 zeros. We'll only have 3 max or mins. So now I'm going to hit second, calculate, and now I want a minimum again, which is 3. And I go over near that minimum. Very tedious, even with a calculator. So just think how bad it would be without. Hit enter, and now scroll to the right of that, hit enter twice, and my relative minimum is, or local minimum is 3.96, comma, negative 43. So 3.5696, 3.96. Boy. Comma, negative 43. Again, an approximation. So let's take a look here. Use the graphing calculator to graph. We did the graph of GS4 x-intercepts. Here they are. Whoops. Here they are. And 3 turning points, which are right here. And I didn't label this one as a local min. So min 0. Actually, it goes 0, minimum, 0, maximum, 0, minimum, 0, and up to infinity. Okay, and so then I can wrap this all up and say the x-intercepts are negative 1.14, 0.29, 1.82, and 5.03. Local maximums at here, local minimum at negative 0.57, 6.51, and 3.96, negative 0.43, or negative 43. Okay, they were a little more accurate with their approximation, but 4/100ths really doesn't matter when you're at 43. And the function is increasing between this minimum, which was negative 0.57, to the maximum, which is 0.11. And that's what it says here, when x is between this point and this point. So it is increasing right here, from here to there. It is also increasing from negative 43 to infinity. Okay, so when x is greater than this x value, 3.96. So it's increasing from here to the right as x goes greater than 3.96, and that's what it says right here. And it's decreasing until it gets to negative 0.57. So that's right here. So it's decreasing when x is less than negative 0.57, and when it's between these two, the maximum and the minimum. So it's decreasing between 1.11 and 3.96. Okay, so hopefully that makes sense to you. So now you should be able to do problems 23, 24, and 26. Hopefully you have a graphing calculator. And if you use Wabbit, WABBIT.EMU, you can download it on your personal computer, but not on the school's Chromebook. Okay, even and odd functions. Now we're going to start talking about that core concept, even and odd functions. A function f is an even function when f of negative x equals f of x. So if we change all of the x's to negative x, it's an even function if nothing changes. the graph of an even function is symmetric about the y-axis. So that means that the line of symmetry is the y-axis, and we can fold it and it looks the same on both sides. Every point on one side would land on the point on the other. And that's how we determine if it's even. A function f is an odd function when f of negative x equals the negative of f of x for all x in its domain. The graph of an odd function is symmetric about the origin. So in other words, we could rotate it 180 degrees. Okay, so if I rotated this function right here, 180 degrees, this point right here, this relative or local maximum would end up at the local minimum, and the local minimum would be at the local maximum, and the end behavior would be the same. Okay, so for an even function, if x comma y is on the graph, the negative x comma y is on the graph, because that's how we reflect across the y-axis. If you remember your geometry last year, for an odd function, if x comma y is on the graph, then a 180-degree rotation will make x negative and y negative. So if this is the point 2, 3, negative 2, negative 3 is a 180-degree rotation of the point 2, 3. So let's take a look at that in the next example. Okay, so here we go. We're going to identify. So if that didn't make sense to you, hopefully you understand this concept after I do these three examples. So it says determine whether each function is even, odd, or neither. There is a chance it's neither. It doesn't reflect in the y-axis, and it's not a 180-degree rotation. That would be neither. So what we do first is we replace x with negative x in the equation. So what that means is we take our f of x and say, now we're going to do f of negative x. And that's going to equal, in every place you see an x, you put a negative x in place of it, and it's going to look like this. And then I say then f of negative x, and then I simplify it. Well, negative x to the third power is still negative x, so that's still going to stay x to the negative 3, or negative x to the 3, I mean. And a negative 7 times a negative x is plus 7. So negative x cubed plus 7, since that is equivalent to negative f of x, then we're going to check that. So how would I explain this? Okay, this would equal negative x cubed minus 7. Oops, I forgot my x here. X. So in other words, if I negate this and distribute, negative 1 times x cubed is negative x cubed. Negative 1 times a negative is positive 7x, 7x. And if you look, what's in this parentheses after that minus sign is what we started with. So that would equal the negative f of x. So if f of negative x equals, I should bring these down, these never change. So if f of negative x equals negative f of x, I'll go back. If f of negative x equals negative f of x, it is an odd function. Continuing, so this is odd. Okay, so I'm going to stop right there and show you the graph of this. Okay, so here's the function f of x equals x cubed minus 7x in Desmos. And if I find the relative maximum, it is this point, negative 1.5 comma 7 approximately. And then if I come down here, the 180-degree rotation, sure enough, the negative 1.5 became positive, and the positive 7 became negative. So this is a 180-degree rotation would land this point on top of here. So the function is going to land right on top of itself at a 180-degree rotation. So it is odd. Okay, so that's that one. And then we're going to do B next. So B is let's see, x to the 4th plus x squared minus 1. So again, we're going to, let's use red, g of x, whoops, g of negative x is going to equal negative x to the 4th plus negative x squared minus 1. Simplify that. Think of negative x to the fourth as negative times a negative times a negative times a negative. And since it's even, it's going to become positive to the fourth. Same with this one, it's even, so it's going to remain positive, squared minus 1. And so now I have g of negative x equals x to the fourth plus x squared minus 1, and that's what we started with. And therefore, this is an even function because g of x equals g of negative x. So if I go back, if f of negative x equals f of x, then it is symmetric about the y-axis, and it is even. So now let's go graph this. X to the fourth plus x squared minus 1 in Desmos. X to the fourth plus x squared minus 1. So I'm going to clear this. X, oops, it was already up, to the fourth plus x squared minus 1. So as you can see, this is symmetric about the y-axis. This point here would end up at here, and the rule says that x comma y becomes negative x comma y. So if I pick this point, say like right there, negative 1.39, or I'm sorry, 1.34 comma 4.02 would become negative 1.34 comma 4.02 if I were able to click on that exactly. Okay. So this is a reflection across the y-axis. So that is even. All right, and now let's do the last one. I'll use green this time. So I want to do h of negative x, and that is going to equal negative x to the third power plus 2. So that is going to equal negative to an odd power is going to stay negative x cubed plus 2. And as you can see, it's not the same, so it's not even. And if I factored out a negative 1, I want to check to see if this would be the same as the original. If I factor out a negative 1, I'm going to get x cubed here. Negative times a positive is negative. Negative times a negative will give me this positive 2. And as you can see, this does not equal this, so it is neither odd or even. Okay, and that's how you do it, because h of negative x does not equal h of x. Okay, so hopefully you understand that, and now do 39, 40, and 42. Okay, this brings us to the end of chapter 4.8. Please do these exercises if you have not done so already. Thanks for watching, and have a great day.